So over the course of the next 2 hours, I'm just kidding. It's so when I timed it, it was about an hour. We're starting a little late, and I'm sure there'll be questions as I go. So if we get to 7:30 and people have to run, I will not be offended. And then yeah, happy to take questions as we go, and I can keep going if people are interested. But yeah, so just as a brief introduction of roadmap. I'm going to give a super quick intro to what stack traces are. Then I'm going to dive into the mechanics of how stack traces are generated. So that consists of walking the stack, performing address resolution, and then querying debug symbols to get function names and line numbers. After that, I'm going to talk about signal safe stack tracing, and then I'm going to talk about tracing C++ exceptions. Yeah.
Can we try this? I'm going to put this one on you also, and then you on Zoom, and I'm going to. And I'll do the audio from my computer.
Okay, perfect.
All right, double mic.
Double mic.
I'm sure I look hilarious.
In stereo.
Alrighty. So to get started here. So I have a simple program. Main calls foo. Foo calls itself a couple times. Then foo calls bar and bar cycle. So I'm going to use this buggy program as a motivating example for stack tracing and various diagnostics throughout this talk. So if I run this program into debugger, the first thing we'll see is we cycle as expected. GDB is awesome and will tell us, okay, we cycle to bar that happened in main.cpp on line 2, and it'll show us the lines where we cycled. Now obviously here it's intentional that we cycle, and it's probably pretty clear why we cycled. Usually it's not so clear, and we would need more information to then understand why we segfaulted. Some of the most useful information to understand why why we segfaulted or why we have any bug is to understand first how we got here, and that's where stack traces come in. So if I ask GDB for a stack trace with the BT command, GDB will print out a stack trace for us. The first frame is a little cut out there on the LCDs, unfortunately. But the stack trace shows us that as we would expect, main called foo called itself a couple times on line 9, then foo called bar on line 7, and then the cutoff frame will just tell us that that the trace originated in bar on line 2 on main.cpp. So this is pretty. Yeah. C++. So this is valid both C and C++ code. I'm using C++ 23 for most of the talk. Oh, is it?
So this is undefined behavior,
but I'm using it as a motivating example for. So I don't know of any. Yeah. So if I turn on optimizations, GCC will it won't actually optimize away this the bug that I've introduced here because it's volatile. Pretty much the compiler won't ever touch anything related to volatile. Yeah. I actually didn't know it was deprecated, so I'll have to. Yeah, I'll have to read about that. Yeah. Oh yeah, I guess if there's any questions from the Slack, yeah, please. Okay. So the BT command from GDB will give us a stack trace, let us know how we got here. BT stands for backtrace. Stack traces are also known as backtraces, call stacks, tracebacks, and various other permutations of those 4 words. If you call it a stack back, you will be the first in history to do so, but I would reckon like most people will understand what you're talking about. So why generate stack traces? So obviously, the example I gave, I was using a debugger to generate the stack trace. But it's useful to be able to generate these programmatically. Most reasons come down to diagnostics, whether it's debugging purposes, error handling, logging, assertions. I initially got interested in stack tracing because I was annoyed that CAssert didn't provide a stack trace, and I always had to rerun my programs in the debugger to understand why the assertion was failing. Another interesting use case for why you might want to generate stack traces are for various performance tooling, like generating flame graphs. In order to generate a flame graph, you have to have some understanding of where you are in the call stack and what's above you. So to generate these programmatically, C++23 introduced std stack trace, and that makes it easy to generate these stack traces programmatically, easy to add useful debugging information to your programs. If that had existed at the time that I needed stack traces, I would have just used that. It didn't, so I started writing a stack trace library. I was running into portability issues with the other libraries that were out there. Some other C++ stack trace libraries include like boost stack trace, backwards CPP, lib backtrace is sometimes used. Some guides online will tell you to use execinfo.h to make a backtrace. Execinfo.h is included with Linux, but it's of course not portable, and then also it requires like you to pass -r dynamic to a compiler to get debug symbols. Question?
Yes, just was curious. Is this stack trace also similar to time travel debugging?
So time travel debugging is something else. That would be more debugger tooling for how to like rewind your program as opposed to just seeing where you currently are. Yeah, and so anyway, I was running into some various portability issues, and so I started writing a stack trace library called CPP trace. So let's hop in. So writing a stack trace library, and I added this tagline, how hard could it possibly be, initially to a later slide, a couple later slides, and then I just realized it applies to the rest of this talk, so I added it here. Start off with the mechanism, or with the mechanics. The first thing we have to do is walk the stack to figure out what function's called what. So a very oversimplified x86 stack here, and I hope not too much information was cut off from the LCD. Okay, that looks fine. Yeah, so very oversimplified x86 stack. Kind of pretending that this is our program from earlier. Main stack frame might be up here. Main calls foo, and then foo's stack frame is over here. And a stack frame is just where the function can put local variables, arrays, whatever other information it needs to store. A function call needs to be able to return to its parent. And so 2 bits of information are stored on the stack to make that possible. First, there's a return address, and this is just an instruction pointer. So when we return, we can return to exactly the instruction that we were executing in the calling function. And then the other thing we save is a base pointer. The base pointer just tells us the base of the current stack frame. And we'll get into that. So we have 2 pointers here. We have the base pointer and the stack pointer. The stack pointer is dynamically adjusted by the compiler as it allocates stuff on the stack. And then the base pointer is just meant to represent the base. It points to where the base pointer is saved on the stack, and then RBP plus 8 is how we would access the return address. So in theory, it says walking the stack and figuring out all of our instruction pointers for the call stack is as simple as basically walking this linked list. And so to return to our example from earlier with this buggy program, if I compile it on Compiler Explorer, we will see, and the gap in the screen is cutting off a little bit, but not too much. So we'll see, for example, main immediately subtracts 8 from the stack pointer because it's allocating some space for itself. It's going to call foo. After it returns from foo, it's going to add 8 back to the stack to adjust that stack pointer back as it deallocates. But what you will notice here is there's no base pointer, as you're mentioning. So compilers optimize as an optimization. They do not emit anything base pointer related. If we want base pointers, we have to specifically request it from the compiler with -f no emit frame pointer. Yeah.
Yeah. All this happened during the runtime.
Yeah. So the compiler is doing this during compile time, but then this is what's actually running. Yeah. So I'm passing. Yeah, so a lot of my talk is going to, yeah, so I guess to quickly back up, no, all good. So the stack trace library I wrote it's meant to be portable with various systems. There is a lot of, platform specific stuff that is required. So a lot of my talk where, platform specific stuff comes in, I'm going to be, mainly using the system VABI and the Itanium ABI. But yeah, so I'm passing a few other parameters or a few other compiler flags here, like f no inline functions, no IPA pure constant. This is just stuff so that the compiler doesn't optimize away all the fun I'm trying to have here, and so I can give good examples. But if I pass -f no emit frame pointer, now we will see, okay, at the start of main, the first thing that's pushed is RBP, and that's us saving the base pointer. And then, stack pointer stuff may continue to happen, but we'll see a lot more instructions happening with the base pointer. Question?
Yes, I was just curious, if you also had like keyboard dynamically allocated memory,
Mhm.
and you were trying to debug a stack crash where stack pointer actually mixed to what's on the key, would that also affect this, or am I assuming something?
So the sort of memory error you're describing would likely just result in a seg fault. And what you would do is, probably run in a debugger, and then you could get a trace back from where that seg fault occurred. And I'm going to talk about tracing signals later on. But yeah, so anyway, so the compiler optimizes away the base pointer. It does this as an optimization. General purpose registers are really valuable, and it's also nice to not have as many instructions, pushing and popping from the stack. So my earlier example of how an x86 stack worked was a little over optimistic. Here's how it actually works. There's no base pointer. RBP could be anything. We don't save the previous RBP, anything like that. We just have a stack pointer that shows us the bottom of the stack. So in order to walk back the stack frames and try to get the information we need in order to do a stack trace, there's no longer a linked list we can walk. So it seems like we're kind of out of luck. But we can't be out of luck. There fundamentally has to be some way to go backwards. The C++ needs to be able to walk back the stack and unwind when you throw an exception. So there must be some way to do this. And the way we do this, the mechanism that allows this, are these error handling frame tables. And this will help us kind of recover the base pointer from the stack. So there's two sections written out to an ELF binary. ELF is the binary file format on Linux. So there's these two sections written out, .eh_frame and ehframe header. If we look at what's inside these sections, we will find that these sections are actually dwarf debug symbols. I'm going to get more into what dwarf is later, but it's just a debug symbol format, and it contains it's usually used for information like here's all the functions in a program, here's where local variables are stored, all that good stuff. But so dwarf is reused here for the tables that are generated that will let us recover our base pointer. And so you can see here those DW underscore, that just stands for dwarf, underscore CFA, and that's going to mean canonical frame address, and we'll get into that in a second. I'm going to explain what all of this means. Question?
Yes, I was just wondering, is there sort of an inefficiency because you have to go to the ELF file in order to get the base pointer?
Yeah, so paying a cost when you actually want to walk the stack, but in turn you maybe get faster runtime because you don't have to maintain the base pointer. Yeah, exactly. Yeah. So yeah. Okay. So to get into what we're doing here, so returning to the x86 stack that I had, so we no longer have the base pointer. We don't have anything that, but we do have what's called a canonical frame address, and that's what this error handling frame table is going to provide for us. So the CFA is very analogous to what the base pointer is. It points to a slightly different location. So in order to access the return address, instead of adding 8 to the base pointer, we would subtract 8 from the CFA. But same purpose, and this is what will allow us to walk back the stack. The output that we get here, so we would expect some sort of, I've been calling these error handling frame tables. The intent is to basically create a table that allows us to, relative to the stack pointer, relative to RSP, figure out where the base pointer is. This output doesn't really look like a table. And so I'm going to get into what this, well, actually, now's the perfect time. So you might notice down here at the very end, this last entry, and Dwarf has a bunch of nodes and then a bunch of attributes for the nodes. So we just have an attribute list here. This last attribute is a NOP. And if anyone is familiar with assembly, you might recognize NOPs. That generally means like generally used to represent an instruction that does nothing. So these attributes, they aren't a table, they're actually instructions. And so in order to understand what these mean, we have to write an interpreter, a virtual machine, to interpret this pseudo instruction set that will tell us how to convert a stack pointer back to a CFA. So to kind of go through quickly what this means, and the monitor cut off my example. You'll just have to trust that the addresses here you correspond to the start and end of foo. So just to prove that I have found the correct information for this function foo that we're going to go through. And this is foo from the earlier example. So I'm still using the same code that we've been using this whole time. So the next 2 bits here. So we'll see DWCFA advanced location. And this is telling us, okay, we're doing something at this instruction, which is right there, and then we're doing something at this address, which is right there. That's the return. And so the last 2 bits, the last 2 bits of information here are this 16 and this 8. So what's happening here is, as soon as we add 8 to our stack pointer, suddenly the CFA is 16 bytes above the stack pointer. And so that's what these 2 instructions are telling us. As soon as we get to this address, any instructions here are going to see a stack pointer 16 bytes below the CFA. As soon as we subtract 8 from the stack, or sorry, as soon as we add 8 to the stack pointer, sorry, the stack grows downwards. So address space goes down, but you typically think of like the bottom address as the top of the stack. I confuse myself a lot on it. So apologies if I've confused adding and subtracting from the stack pointer here. But so as soon as we add 8 to the stack pointer, then again, the stack pointer is going to be 8 bytes below the CFA. So all this information and interpretation, and we're finally able to recover essentially the base pointer that the compiler emitted from this output. This is a very simple example. This instruction set is a lot more complicated. It can do things like encoding other registers. If you have like a VLA on the stack, this output will look a lot more complicated. But to keep going here, oh yeah. So this is complicated. So obviously I didn't write an implementation of this for my library. So the way unwinding is done in practice, there's a few functions you can use. So underscore underwind backtrace from libgcc is an internal error handling routine used by GCC for handling exceptions. So my library takes advantage of that for walking the stack. There's also a backtrace function from execinfo.h, and there's also libunwind, which is a dedicated library for stack walking. On Windows, there are two built-in functions, capture stack backtrace. And when I was talking earlier about a lot of permutations of 4 words, capture stack backtrace is pretty good in terms of having, at least 3 of those. And then stack walk 64. And you might think like, oh, how nice, Windows gives you built-in functions to do this, it must make it easy. So obviously this is too small for you to read, but just to share some of my pain with you. This is an implementation of stack walk 64. You have to juggle all the registers yourself, and there's a function you can use to get like a stack context, and it'll contain some registers, and then you call the callback again with the updated registers, and it'll get the previous frame, stuff like that. Of course, because it's Windows, Windows has to have a lot of prickly edges around any API. So the get context function isn't implemented on some architectures, so you have to do some inline assembly. It's a lot of fun. But yeah, anyway. So now we're at the point of understanding how to walk the stack and how to get our instruction pointers. There's one little subtlety to highlight here. So suppose we are generating a stack trace from our segfault, and our segfault happens on line 2 here, where it moves 1 to address 0. Suppose we were, producing a stack trace here. We had probably hoped to see, okay, I want to see this address. I want to see this address where foo calls bar. I want to see this address where foo calls itself, and see that a couple times. And then I want to see this address where main calls foo. It turns out that the addresses we actually get are almost that, but the call instruction doesn't save the address of the call. It saves the address of the next instruction because it's the return address. That's the instruction we're returning to. So there are a couple stack trace libraries out there that mess this up, and they inadvertently produce incorrect line number information. And Compiler Explorer is great for this because it will do color coding of what these lines correspond to. So for example, we can see here in main, this shade of gray corresponds to the foo call, and then this shade of gray corresponds to something else. So if we didn't, properly adjust these resulting instruction pointers, we would get the incorrect line number when we're resolving this address. So we need to just back up the instruction pointers to get to the previous instruction everywhere that's not where a signal handler happens. And that's just what would happen when we segfault. This is a little complicated because actually it's impossible on x86 because instructions are variable length. So fortunately, the way you can do this is by just subtracting 1 from your instruction pointer, and the debug information emitted by the compiler is such that as long as, even though you're looking up an instruction pointer that isn't an actual instruction address, as long as it's in the instruction, you can still find it. Okay. I'm going to drink some water. Does anyone have any questions before we move on to the next section? Yeah.
Is there any sort of processor architecture that they kind of, instead of having the stack go down, kind of have the opposite, that the stack actually increases?
I'm sure there are, but I'm not familiar with them. So Matt would know more than me. Yeah.
ARM can go either way.
Okay, ARM can go. Okay.
Particular thing is just register.
So ARM can go either way on that, and then either way on NDNS. Then yeah. Okay. Yeah. All right. So now we have a bunch of addresses. The next thing we need to do is resolve those addresses. So at the moment, all we have, and I've grayed out most of the stack trace, which the shade of gray isn't coming through as clearly on the LCD as I had hoped. But at the moment, all we have are these numbers. So the next thing we have to do is, these addresses are obviously in the program's memory space. This is not how the addresses will appear in the binary itself. So we need to reverse this address back to what would be in the binary. So we need to find the offset relative to where this code is loaded into memory. These addresses are randomized too, so that introduces some extra complexity there. This number doesn't do us a whole lot because we have to actually go and load debug symbols from the binary. So we need to find the path to that binary on the file system. And then the binary itself is going to have more offsets that we then have to take into account. So that's what's in store for this section. And I'm going to blitz through most of this because a lot of it, isn't horribly interesting. It's just a lot of manual and careful juggling. So on Windows, there are some helpful built-in calls to do this. You can get module handle exa because Windows function calls are always named in that fun way. When you get module handle, you can pass in the instruction pointer, and that'll just tell you what module it corresponds to, and the module handle will be the base pointer of where it's loaded into memory. And then get module file name, well, that'll just tell you what file on disk it corresponds to. On Unixes, there's dladdr, and you can use that to get information about where the object is loaded into memory, and as well as the object path. And I put a star next to it to remind myself that that's not always the case. Because with glibc's implementation of dladdr, if you look up an address in the executable that's running, it uses argv0. Argv0 is not always the path to the binary. It might be a relative path. It might be something completely non-standard if someone invokes the program weirdly. It might also be modified by main. So the way I learned that is I was trying to use the library I wrote at work. And at work, we invoke things weirdly. With non-standard argv0s. Perfectly reasonably. So that's how I learned about that. So there's an alternative dladdr1, which is great naming, and that's supported on most glibc versions made this century. I forget when it was added. It's been in there for a while. So anyway, so dladdr1 will give us the information we need. It's not the fastest way to get the information. So if possible, what we'd like to use is a call called _dlFindObject, but that only exists since relatively recent glibc. So there's a lot of dynamic detection a library might want to do to find the best option to do this address resolution. Nothing can be as easy as you would want. I mentioned base offsets earlier. All binary file formats have some base offset that you have to take into account when looking up addresses in the binary. So for example, if I was in the earlier example, if I was taking the runtime instruction pointer for main, and I subtracted it from where the binary was loaded into memory, I might see something like OX100. It's not going to be in the binary as address hexadecimal 100. I'm going to have to add in some offset, and that might be hexadecimal 4 million. And that's how it'll appear in the binary. So all binary file formats have these. And so when writing a C++ stack trace library, you then have to write parsers for all these file formats. So PE files store this in a field called image base. ELF files store this in 2 places. The program header table has 2 fields, p_virtual address and p_offset. And then mock-O, which is the file format used on Mac, which is definitely the coolest name. Well, actually, ELF is pretty cool too. They have an attribute, the VM address for the __ text section. On mock-O files, there can be multiple text sections, and I think the correct thing to do is just take the address of the first one, and it seems to work. But I didn't find any documentation about that, so, but it works. I haven't gotten a bug report yet, so. Yeah, so that wraps up everything for address resolution. The next thing we need to actually do is, or the next thing we need to do is take these addresses we've resolved and now actually query the debug symbol. So what we want is a line number and the name of the symbol. So on Windows, there's a library called dbg help, which can be used to access debug symbols in PE files. On Unixes, and then also used by MinGW if anyone has used GCC on Windows. This is called Dwarf. Dwarf, obviously, very fun name, probably named after Elf. They have a fantastic logo. I think the C++ standards committee needs a equally cool logo. I don't know who to take that up with though. But all right, to get into this, so dbg help, I had hoped that this built-in library to Windows would make it super easy to access all the information that I wanted. It makes it kind of easy, at least in terms of accessing a function name and then a line number. But if you want to be able to provide arguments, and I think having a full signature for a function is really important in C++ since functions can be overloaded. In order to get that information, you have to walk basically an AST-like structure encoded in the debug format. There's a couple of very prickly edges, like the way template arguments are handled is very weird. It's very difficult to differentiate a pointer from a reference and how this information is stored. It's impossible to differentiate, differentiate an R-value reference. And then the way CV qualifiers are stored is also weird, and I'm not sure I ever figured out a perfectly correct way to handle those. But I eventually found a reasonable-ish way of doing it that provides decent symbols. Since I mentioned std stack trace earlier, the MSVC implementation of std stack trace, if I remember correctly, doesn't print the full signature for functions, probably because of limitations of the debug format. Question?
Yes, it's the reason why the R-value references are kind of difficult is because when this is actually kind of more than like 20 years old or so, and like there were no R-value references at the time.
Yeah, and I mean, as far as the compiler is concerned, everything's just a pointer. So references are encoded as pointers, and then there's some other function they added at a later time to check if the pointer is actually a reference. But yeah, yeah. Over what? So that's a great question. Yeah, so there was allegedly an option with dbg help to get a mangled symbol. But when I say allegedly, I was never able to get it to work. So yeah. Well, so demingling is what I use for on the Linux side of things. So I'll get into that next. So on the Linux side of things, we have Dwarf, which is just fun to say. So Dwarf is a tree linked list type structure in memory. We have a bunch of nodes. Those nodes have children. All Dwarf sections start with like the top level node is a compile unit, and that roughly corresponds to a .o file. And then we'll see here, okay, we have a subprogram node, and it cut off all the fun stuff I wanted to show, but this is the subprogram for main. This next subprogram is foo. And you can see here foo's formal parameters, what it's called in Dwarf, but the parameter n is saved here. And you can see this tag here, DWAT location, and that's going to say op fbreg -20. And so that's telling us that I believe n is 20 bytes below the base pointer. And so that's what tells the debugger how to then find n when it's running. So if you ever want, so I don't in my library. Someone actually asked about that. But just for some context, if you ever wondered how the debugger showed that information, that's how it can. Yeah. There's no way to get the line numbers or function name without dwarf. So, well, if you know of a way, yeah, please let me know because because I cannot find a way. Yeah, so DLSim can work for getting a mangled name, but that's only if you like compile with dynamic like export information. And so that's when I mentioned rdynamic earlier and the exec-info solution, you have to compile with rdynamic to have those symbols. If you want, yeah. Oh yeah, this has a cost to it, but ultimately, I'm not too concerned about cost. I was just trying to make a stack trace library that actually allowed you to stack trace an arbitrary program, ideally without having to add rdynamic or anything like that. Okay, so we have our tree linked list type structure that gives us a lot of information. Oh, and since you mentioned name mangling earlier, there's a mangled name here, and this is a abstract origin tag, and that's just telling us that like the actual information for that function is going to be later, so that has to then be looked up separately. But we can get a mangled name, and then my stack trace library uses that mangled name to provide the full symbol. To get the line information, line info is stored in a separate table. And similar to earlier with CFAs, the line table isn't actually a table, it's a DSL instruction set. So you have to write an interpreter to interpret the line table language to build up the line table, just to get a line number. I'd never actually had to implement one of those, thankfully, because I was using a library for accessing dwarf symbols. libdwarf and libdwarf has an implementation that I just leached off of. Question? Or?
Yes, I was just wondering,
Mm-hmm.
are you kind of demangling the name from your application, or is that demangling in code?
Yeah, so the compiler spits out the name mangled according to the ABI, and then my program uses, or my library uses, I believe the header is a CXX ABI, and then there's a routine there you can use, or you can call to demangle that name. So I didn't have to implement a demangler or anything. That would have been a pain. But yeah, so all this work, what do we win? There we go. Finally, we can produce a stack trace. So there's one, or I guess the next interesting bit here is this is what happens when we run our program in debug. What happens when we run in release? Oh, and quick note here. So the whole time I've been using this simple program main that calls foo calls itself a couple times, foo calls bar, and then bar seg faults. And this to produce the stack trace, this is not the seg faulting version. I just put in a call to my library to generate a stack trace at bar. I'm going to get into some more practical examples later, but just to show that we can fundamentally produce a stack trace. Okay, so this is debug. What happens if we run in release? If we run in release, we will see that the compiler optimizes away all the function calls that we made, and we see that the stack trace was generated from main.cpp line 5 in main, but line 5. Oh, and I might have ran with different versions of the code here. Up in the debug version, it said that we were tracing from line 4 in bar. Just pretend this is 4. Otherwise, that's a bug, so I'll have to look into that later. But anyway, so it's a little misleading to say, okay, we generated a trace from main, but on this line that's not part of main. So it would be nice if we could, give some information about the fact that a bunch of inlining happened here, so we can give a more accurate stack trace. So dwarf actually makes this really easy. So if we look at the dwarf output from our optimized version, we will see, we have our subprogram main, and then the first child within that node is an inline subroutine, and this is telling us, okay, foo was inlined into main. That's what we'd expect from any good compiler, and then it'll include information about about what file that or where that call happens. So what file, line, column, all that good stuff. And that'll tell us, okay, the foo call was at this location and it was inlined. Another bit about dwarf that I forgot to mention earlier. So the way we actually match an address to a location or to an entry in dwarf, there's two attributes here: low program counter and high program counter. And so we can check to see if the address we're looking for is between those. Dwarf doesn't make anything, well, dwarf, it tries to be very flexible. The compiler doesn't make it easy to do anything because it's not always as simple as just checking if you're between two addresses. Dwarf can also emit range lists. And so then you have to walk through a range list and check if you're anywhere in there. Sometimes you get both a range list and a low program counter, and that's meant to be an offset in the range list. So then you have to take this offset into account. Range lists work very differently between dwarf 4 and dwarf 5. So there's a lot of complexity, with trying to handle this stuff. But for the inline subroutine, we'll see the exact same range information. So if we're looking up an address, we can check, okay, is our address actually within this inline subroutine? And then that can help us recover the information about what was inlined where. So my library can parse through this, and to I guess highlight one place that my library is still relevant over STD stack trace. Current implementations of STD stack trace don't handle this inline information. But so if we look at what we generate and see what we want, we can recover, okay, foo was inlined into main, and then bar was inlined into foo. And so that gives us much more helpful information. And we can see, okay, yeah, the stack trace was generated at line 4 in bar, and that makes a lot more sense. You might notice that there were a lot more calls to foo up here than in the second program. That's of course because all of that recursion was optimized away. So nothing we can do to actually reflect that recursion, but at least we can better illustrate how we got from main to bar. Question?
So in the debug version, when we have like all the calls of foo,
yeah,
I don't imagine it like stores in the register like how many times it's called and so forth. So how does it, apart from just inspecting like the height of the stack, how does that like dwarf like special instruction set let you calculate how deep into this?
Yeah. So I mean, every call of foo is its own stack frame. So fortunately, that dwarf language doesn't have to do anything fancy. It just tells us, okay, if you're at this instruction within the function, here's where you are relative to the CFA. And do you have a question?
Yeah, is this also kind of similar to what's happening on Windows if you're doing debug versus a release mode, that there might be some inlining?
Oh yeah. Any modern compiler will do a lot of function inlining. Yeah. And then with dwarf symbols, we can recover some information about that. I never found a way to get that with debug symbols on Windows, but there might be a way. A couple quick more notes on, a couple more quick notes on dwarf. So there's a lot of lacking when it comes to tooling and documentation. A lot of figuring this stuff out was trial and error, saying what GCC was emitting, saying what Clang was emitting, saying how they differed. Dwarf 3, 4, and 5 are all pretty different, and they can all be found in the wild. Dwarf 2, I think, is still technically supported by compilers, but I've never seen it in the wild. There's something called GNU debug link, There's a lot of efforts to like separate debug symbols from the binary itself. The main concern is link time. Having all those debug symbols in the binary and having to link those all in and handle changing of addresses and whatever, that actually slows down the link time a fair bit. So there's a few effort. Oh, and it also blows the binary size, of course. So there's a few efforts to separate that information out. One is called GNU debug link, and that's basically a special, let's see, I think it's a special section in the ELF file that actually tells you, okay, the debug symbols you're looking for are in this other file, and then you have to go read this other file. Dwarf 5 standardized something called debug fission, which is a way to, which is a way to actually say, okay, go get the debug symbols from the .o file you built, and then there's a lot of weird address translation stuff that has to happen there because there's no adjusting of the addresses done by the linker. So debug fission can improve link times a lot, but it's very complicated to work with. It was standardized in Dwarf 5, but GCC and Clang support it in Dwarf 4. You might wonder how they supported it in Dwarf 4. They did it by creating non-standard implementations that work ever so slightly differently, and neither of, so there's, well, frankly, it's a nightmare to deal with. Fortunately, so I use libdwarf, as I mentioned. I found a number of bugs in libdwarf as I've been working through this. The author of libdwarf is amazing, and he's been super receptive with all the issues I've created and super responsive. libdwarf is one of those XKCD style libraries that like a lot of people depend on, and it's just maintained by some random person in Nebraska. I don't know if he's in Nebraska. He might be. And then there's a bunch of other vendor extensions. So on Mac, there's these things called dsym files. And so in order to find your debug symbols, you have to go look up I call it a dsym file, but it's actually a directory. And so you have to go a couple layers deep into this directory to find the debug symbols for your program. And so that's fun to deal with. But that about sums it up for debug symbols. So hopefully this can serve at least as a little introduction to some of the work required to get to this point of producing a stack trace. We are coming up on an hour, so of course, if anyone asks to leave, I will not be offended. The next thing I want to talk about is signal-safe stack tracing. So our earlier example where we're segfaulting, generally, if you segfault, you have to rerun in a debugger to get any information at all about about why you segfaulted. That can be annoying. Sometimes it's hard to reproduce in the debugger. So it'd be very nice to be able to programmatically generate a stack trace when we segfault. So how can we do this? Well, when we segfault, the operating system sends your program a signal. That signal is sig-seg-v. Your program, and that signal will then go on to kill your program. We can hook into that signal, and the LCD might cut off some interesting parts of this, but ultimately we can use a system called sig-action, and that will allow us to register a signal handler for what happens when sig-seg-v is sent to our process. And here I just have a simple signal handler here that will write out sig-seg-v occurred, and it'll write that out to std error. You will notice that I'm not using std print, std iostream, not using printf, anything like that. Signal handlers are very restrictive environments, so it would actually be dangerous to call any of those functions. The only way you can print something out is by using the right system call directly. And then at the end, you have to explicitly exit out of your program, because if you've made a sig-seg-v handler and you don't exit, then you will get into an infinite loop of segfaulting, which is hilarious to watch. Question?
Well, I guess you sort of answered it. So what's the worst thing that can happen if you call like just the normal print function?
Oh,
Like, you already segfaulted. What's the worst thing?
yeah. So
I assume if you could be caught
Yeah. So you could segfault during your segfault handler. You could get into a deadlock with yourself. That's typically the worst that would happen. Yeah.
Actually, I went to a talk in DEF CON.
Yeah.
Basically, segfault handlers.
Yeah.
Like basically modify basically already running code.
Interesting.
Basically switching out memory,
Huh.
linking of already running code. So basically, you could basically hijack a program that's running.
Jeez.
Okay, so the worst that can happen is you get hacked.
Apparently, yeah. That's terrifying.
Excuse me, right?
Yeah. Yeah, so you can segfault in your segfault handler. I don't actually know. I've never been in that situation. But yeah, great question. So segfault handlers are really restrictive environment. Well, any signal handler is a really, really restrictive environment. The reason it's so restrictive is that, unlike other multi-threading situations, and to be clear, this isn't a multi-threading, but it's kind of similar to multi-threading in some ways. But the difference is that you could be interrupted at any point in your program. So you could be interrupted while you're in the process of acquiring a lock. You could be interrupting yourself while you already hold a lock. And then if you try to take out that lock in the signal handler, you will either crash or get into a deadlock with yourself. If you call malloc, you could be calling malloc while malloc is in some undefined indeterminate state. If you touch any global state in your program, that could be happening when your program is in weird indeterminate state. So it's super easy to, crash, deadlock, get hacked while you're in a signal handler. But what can we do? Actually, yeah, more examples of what we can't do first. So no allocation, no buffered I/O, no locking, and in general, no fun. Question? No. Your program just has to hard exit out. Yeah. If you've segfaulted, something has gone horribly wrong, and if you called destructors, you would probably do more damage.
That's one of the reasons why you use _exit there rather than.
Yes. Yeah.
You just need to literally kill the process. Don't try and do any cleanup.
Yeah, and very good call there. So we want to do a signal safe stack trace, but this is a really restrictive environment. So what can we do? So we can use the open read and write system calls. So we can do some I/O. We can touch global state very, very carefully. And the question, of course, is it possible to do a signal safe trace? Well, one option is in a signal handler, we could collect a stack trace, carefully write it out to global state. And then later, when we're not in a signal handler, then we could go and resolve that trace and print it out and handle it accordingly. That's not really an option in a segfault handler, because with a segfault handler, you have to exit. So what else can we do? And I'll wait for that to come up. So there's a couple other system calls we can use. We can duplicate file descriptors, we can create pipes, we can fork, we can exec, and we can wait. So if anyone's familiar with Linux systems programming, you probably have a decent idea of where I'm going with this. It would be possible to do a stack trace in a signal handler in a signal safe way, create another process, send that information to the other process, and the other process isn't in a signal handler, so it doesn't have the same restrictions. And so that is the one and only way that I can find. Well, not the one and only way. It's the one and only practical way I can find to do a signal safe trace. Because you can open read write, like it would in theory be possible to load debug information in a signal handler and do all that fun stuff. But it would, it would require rewriting the entirety of my library and the entirety of libdwarf just to support this, and that would be a lot of work. So some other libraries have tried to support stack tracing in signal handlers, Boost Stack Trace and Backwards CPP, and they actually both get this wrong. Backwards CPP is just completely unsafe. Boost Stack Trace had an interface where they tried to make it possible to write out to either a file or another process, and they actually no longer advertise that API because they realized it was unsafe. To actually do the trace, and I called this unwinding, but I should have called it walking the stack. So first we need to walk the stack. The only signal safe way to walk the stack is libunwind. And libunwind is awesome for providing an interface to do this. How they do it signal safe, I have no idea, because they have to be loading those EH frame tables from the binary. But it works. Then for address resolution, only _DL find object is documented to be signal safe. I can't tell if DL_ADDR1 is signal safe. It takes out some locks internally, but they're like pthread recursive mutexes, so it might be safe. But but it's not documented, so I don't want to try anything related to it. The one downside here is DL_find object is very, very recent. It's like glibc 2.35, which was like only a couple years ago. But so yeah. So this is, as far as I can tell, the only way to get like the fundamental information we need to do a stack trace. So like the fundamental information we need, only the process can walk its own. Well, I was going to say only the process can walk its own stack. I guess another process could do what a debugger does and kind of hook into the process, but that would be a pain. Only the process can understand where everything is currently mapped within the process. So at the very least, we have to do this walking, and then we have to do the mapping, and then send that information off to another process that can then go and do the resolution and open the file, open the binaries on the file system and whatnot, unless you want to write a debugger. So in CPP trace, the interface that I've created for, well, I've created an interface for the two fundamental operations that need to be done, and then kind of everything else is left to the user, but I have some examples of how to do this. I realize the code is small. I've annotated it here. These two calls at the top are where we're actually walking the stack, and there's a special safe interface to generate the trace that doesn't like create a vector or anything, because of course if you create a vector, you're unsafe. All this down here is calling fork and exec to spawn out a new process, and then it's also setting up pipes. And then down here is where we're actually asking CPP trace to resolve just the bare minimum information about stack frames, and then it's writing this over a path to the other process. And then eventually we just wait PID for that process we created, and then wait for it to print everything out, and then we exit ourselves. The other side of the pipe is way simpler because we aren't in a signal handler. So I use fread instead of syscall read. Very nice to be able to do. But yeah, so just read a frame over stdin because that's where I created the pipe to. And then just the interface is you resolve the safe object frame into a real object frame. And the object frame is like almost everything about a stack frame, except it hasn't resolved the debug symbols yet. But yeah, so you can resolve a safe frame into an object frame, push that into an object trace, and then later just resolve that object trace, and then you have your stack trace. So what did we win? Yeah.
So what is
The CPP trace is the stack trace library that I created for C++. Yeah. So what did we win? Well, we won a stack trace when we segfaulted. So the signal handler I created prints out that a sig_seg_v occurred, and then everything else here is that second process that I created, and this is taking all the safe object frames. That's taking the information like it happened at this resolved address, it happened in this file, and then it's actually going and doing the debug symbol queries and all that fun stuff. Yeah, question.
Yes, if this was on a threaded,
Mhm.
threaded function, would it kind of show like where the where the threads were in the stack trace?
That's a great question. So so this will only show the thread that segfaults. I haven't done anything to try to trace other threads in the process, but that would be a cool thing to do. I looked into it briefly. As far as I can tell, the way you would do it, you actually have to use signals. You have to like call sig, like I believe there's 2 user specified signals you can use, like well, they're 1 and 2. You can do something super hacky there to create a way to trace other stacks, but I haven't touched anything related to that. Yeah.
Yeah, I'm just wondering if you take a name,
Mhm.
then it works for any C++ version.
So my library is C++11. I figured that was a reasonable base to support. I don't know if anyone here is on C++98. I don't see any hands, so I think everyone is safe. Maybe a shrug in the back, but a little bit of C++98.
Legacy code.
Okay.
Yeah, but.
Yeah.
Viable.
I see. Yeah. Or yeah.
Another question about
Mhm.
the,
Yeah.
just return, does it go back and
Y-
not do anything?
So if you return from a signal handler and it's a segfault handler, then you get into an infinite loop of segfaulting because the compiler just tries to run that instruction that segfaulted again.
Okay, for it,
Mhm.
returns -1 to the parent.
Oh, yeah, yeah.
Process when it fails.
Oh yeah.
So if you go back, it's like.
Oh yeah, yeah, yeah. And sorry if I misunderstood your question.
In the if statement,
Um,
line 25. Oh, yeah, yeah. Are you just returning and that just.
Oh, you might have found a bug.
Yeah.
Yeah, well done. I never tested in a situation where fork could fail. So it's not a bug in my books. Yeah, question.
Kind of a little bit, the one slide here, that's after this one.
Mhm.
Is this kind of designed somewhat as an infinite loop, except that it kind of breaks off?
Yeah, so the parent process, the one that's doing or handling the signal, it closes the pipe and then fread just fails. So we break out of the loop here, or actually no, we break out here. Yeah, yeah. This one's the error case. Yeah.
You also you break out two places, but that's only to kill the loop, and then print out trajectories. But if everything is working properly, this would be kind of like a infinite loop.
So the parent process, and I'm going to go back to the segfault handler here. So it calls close twice, and it's closing both ends of the pipe that was created. So that's the parent process's way of saying, okay, there's no more information coming over this pipe, and then in the tracing process, when fread tries to read stdn after it has been closed, then fread is just going to return 0 because it's done. It has reached the end of the file. Yeah, question.
Yes, but when program segfaults,
Mhm.
the thread that segfaulted guaranteed to receive that segfault.
So I believe so. That's my understanding. I'm not 100% sure though. Yeah. Yeah, question.
I feel like I've heard before that a while true is undefined.
It is undefined behavior if there's no side effects. Here we have lots of side effects though. Yeah.
So you said if you return, it will attempt to execute the segfaulting instruction again.
Mhm.
So that implies it's possible to fix the segfault from the segfault.
Yes, and so Perl actually does, or if I remember correctly, Perl is the offender here. So Perl catches sig segfault and it maps pages below the stack. So that's how it can have a dynamically growing stack, larger than the normal multi-megabyte limit.
It's also used in things like emulators and things. You page protect memory, so that you notice when something modifies it, you can patch up what you can take. You can notice that it's become dirty and maybe take effect later on.
Yeah.
So it's the restrictions and the segfault handled by the kernel or
The segfault, or sorry, the instructions of the segfault handler, or the restrictions.
handled by you, right?
Yeah, really handled by the programmer. And Matt and I actually talked briefly about like whether there were any static analysis tools to verify a signal handler was safe, but I don't know of any.
So
Yeah.
it's really just your choice. You can't just
Yeah, so you can put unsafe code in a signal handler, and it might be fine 99.999% of the time. Yeah.
In the else if res not equal to 1, is that kind of just kind of undefined behavior, or is that something that could happen?
It is possible to get a partial read. At least that's my understanding. I forget the cases where it could happen. I think it would mainly be like if the end of file were reached before all the bytes you requested.
you get 0, right? Because you wouldn't have read a whole one.
Yeah,
You'd have to read it in units of bytes. So that it
Yeah,
goes
you-
into the-
yeah. I would have to double check the specification. This might have been some FUD just like trying to make sure that it was 100% safe just in all cases. But yeah. Alrighty. So okay. So what did we win? We won we won. Yeah, I'll get to that in a sec. Yeah, I was just going to go over this real quick. So what did we win? We won a signal safe stack trace. You can see here that first frame that's captured is actually the signal handler itself. And then there's another frame here that's something inside the libc, and that's going to correspond to like libc's implementation of signal handlers. The main frame is right here between the two screens that you can't see. But yeah, so we have a signal safe stack trace at great effort. There's one pitfall here. The implementation that I showed is not perfectly safe. There was a bug that was correctly identified, but there's another bit of unsafety here, and that is shared library calls. Shared library calls are not signal safe. The first time you make a shared library call, that shared library might have to be loaded off the disk, might have to be loaded into program space. I forget if it's a standard library or whatnot, but some of the indirect calls might have to be resolved as well. So a shared library call is not safe if it's the first time you're making that shared library call, and assuming that you also haven't manually unmapped the shared library from memory, which is something you can do. I forget it. It's not DL. It's the opposite of DL open. I forget if it's called DL close or whatnot. That would be the intuitive thing. So just to work around this pitfall, you have to like warm up whatever shared libraries you intend to use in a signal handler. So I'm kind of assuming that libc is warmed up because everything has to call libc before main libc stuff happens. But yeah, so just a simple warm up CPP trace function to make a couple CPP trace calls, and okay, by then it should be warmed up and loaded, and then it's signal safe. So now it's truly signal safe. All right, any questions before? Yeah.
Could you actually, like, if you're calling like third-party libraries that are shared libraries, you try to before the executes, try to create like an object, a global object or something like that, that would be running in order to get those libraries loaded?
Oh yeah, like a global initializer. Yeah, absolutely. And I just put the warm up thing at the top of main, but there's a couple good ways to do it.
It's only the call for the libcpp trace make it that it needs to warm up.
Oh yeah, yeah, exactly. Yeah. Okay. So the next part I want to talk about is tracing C++ exceptions. So if I return to the earlier program, and I have, instead of segfaulting in bar, I throw an std runtime error, and then I run this program, we'll get kind of a similar conundrum to what we had with a segfault. We'll run our program, we'll get a what that says foo, but not a lot of information about why we crashed here. Part of that, of course, is my fault for not putting a descriptive error message. But also, like, it's not uncommon that you get an error message that doesn't tell you much. For example, like if you've ever had an std bad variant access or std out of bounds error, there's lots of times where an exception can get thrown, it could crash your program. You have to then go run in a debugger to try to understand what went wrong, and you have to try to reproduce in a debugger, and it's a hassle. Most other languages by default would give you a stack trace when an exception is thrown. C++ is unique. So what can we do here? So one thing we could do is we could create like a custom runtime error class or a custom exception class that generates a trace during construction. So when you construct this error to throw, it will generate a stack trace. And then if we just run this simple, the implementation I threw together, hang on. Sorry, there's a little lag with the screen. So the implementation I threw together here was just super quick and dirty. Generating a trace can be slightly expensive, so maybe you don't want to just do it the way I did.
CPP trace supports what are called raw traces, and that's just like a vector of instruction pointers. And so those are meant to be like super, super lightweight trace objects that you could then resolve the debug symbols of later. But anyway, so just a super, super simple example for illustrating the proof of concept. And then we run our program here, and we have a beautiful stack trace about where foo was thrown from, and hopefully this may be enough information to help us debug without having to reproduce in a debugger. But this only works for exceptions that we control, exceptions we throw and can use this custom exception type with. It would be really nice to be able to trace all exceptions. C++, I mean, one reason C++ doesn't do this by default is that everything is supposed to be zero overhead. So we'd like to opt into any overhead. The question though, the question just comes down to whether this is possible. Like there's no way to globally hook into every throw that happens. Like there's plenty of macro things you could try to do, but there's no way to hook into like any exception throw that's out of your control. And of course, by the time you get to the catch, like you can generate a stack trace, but the stack has already been unwound. Stack frames have been destroyed. There's no recovering where the exception happened and how you got there. Yeah, question.
Just was wondering, I think I was hearing that there were some ways where they are trying to make exceptions less overhead, but would that actually affect this kind of getting the stack trace and the exception?
I'm not familiar with them, so maybe. And I'm going to, I mean, the sort of setup I showed earlier where you generate a trace in the constructor, that probably wouldn't be affected. What I'm about to show you might be affected. So we want to walk the stack when an exception happens, but by the time we get to catch, it's too late. So it seems like we might be out of luck. But there's some good news. The stack is walked twice when an exception is thrown. It happens, the stack is walked, the two times are first a search phase, and that's where the runtime searches for a catch that actually matches the exception that was thrown. So if you've ever written a catch that's like specifically for a runtime error or specifically for a system error or whatnot, the search phase is how the correct handler is actually identified. It uses runtime type information to do that. And then once it's found an appropriate catch or maybe no catch, it either unwinds the stack and calls all destructors as appropriate and all that fun stuff, or it jumps to like std terminate and just kills the program if there's no appropriate handler. So the fact that the stack is unwound twice gives us a potential way to generate a stack trace. We just have to hook into that search phase. There's a C++ proposal paper out there, P2490, called STD, or called Zero Overhead Exception Stack Traces, and it provides, or it suggests like an attribute with stack trace that you could put on a catch and then call STD stack trace from current exception. And the mechanism proposed in the paper for getting stack traces with zero overhead on all exceptions is this hooking into in the search phase. Yeah.
Just was curious, if you're going to do these the unwind, if you basically have a function that's called no except, or that's declared as no except, would it just go up to the no except function? And then call the STD terminate?
So yeah, so sometimes like when it's walking back in the search phase and it hits a no except function, it actually says, okay, we're done. I'm just jumping to terminate. I'm not walking the stack back any further. And so no except can actually interfere with with the stack traces from my library, because the error handling frame tables that we need to get the CFAs, those are sometimes omitted. Someone opened a bug report on my library due to this happening on ARM. GCC was omitting the error handling table. It didn't happen on x86 though, which was fascinating. But okay, so I'm going to try to kind of quickly go through how hooking into the search phase works. So as I mentioned earlier, the search phase relies on runtime type information, and that's just these type info structs. There's a method in type info. It's a virtual method called doCatch, and this is in libstd C++, but the way it works in lib C++ is very similar. And this is just a method called during the search phase where the runtime is asking a type or a type info object, do you match this type being thrown? As a fun tidbit, the way type info equality is checked is first it checks like if the pointers in memory are the same, and then it just does a string compare on the type name, which, perfectly elegant. So our strategy here to create a signal safe stack trace, hook into the search phase, use some like custom type with custom type info to do so. Is this undefined behavior? Absolutely. But it's for a greater cause. So no, then justify the means. But also, like, this is pretty well specified in the Itanium ABI. Both the fact that that an exception does this two-phase lookup or to lookup and then unwind, as well as the way, like the layout of the vtables for the type info structs is also specified by the ABI. So this ends up being like pretty well defined. But very undefined. Yeah, question.
Yeah, I was just wondering, is the type info that you're getting, is that mangled even though you don't really care if it's mangled?
Yeah, type info is mangled. Yeah. So I've implemented, some support for this strategy in CPP trace. It unfortunately requires a special try-catch macro. It looks ugly, but it works. And it does the instrumentation here to actually hook into that search phase, and then it provides, a way to get the exception or get a stack trace from the current exception. Just to show like what the macro is doing under the hood, and Compiler Explorer has a preprocessor tool you can use to see what macros expand to. But so it's just inserting actually a second try-catch here with a special interceptor type. And then the library modifies the type info for the interceptor type so it can hook into that doCatch function. Just to briefly go over what that looks like. So there's a type info object for this interceptor class. That type info object, type info is a polymorphic class since interceptor itself is a class. The specific instance is going to be a type info for class or whatever libstd C++ calls it. This class is going to have a vtable pointer and then a name, as I mentioned. There's going to be a string compare. But so it's going to point to a vtable. We can find our slot here where that virtual call would happen. We can hook into that on lib C++. And sorry, I'm going to speed up a little bit here for time reasons. Lib C++, it looks exactly the same, but it's called can-catch. The key is that it's in the same slot in the vtable, so we can do the same modification. One interesting note on lib C++, there's these two no-op slots. They're just functions that do nothing. The reason they have those there is to be ABI compatible with libstd C++. So the actual hooking process is mainly manual work. You have to clone the type info vtable. You have to hook the function. You have to remove read protections from the type info object because type info is in read-only memory. Then restore protections. In CPP trace, all of this is opt-in, so this only happens when you include a specific header. And I'm going to skip over that slide. I'm going to skip over that slide, sorry. But so what do we win at the end? We win a stack trace for a normal STD runtime error with no extra implementation. And this is, there's a little footnote about zero overhead, but this is basically zero overhead. And this is as a library implementation. It could be much better if it were merged into the language, if that proposal paper was merged in. So I'm holding out hope on that one, but we'll see. You'll notice there's some extra frames above where we actually threw our exception in bar. Those frames correspond to internal error handling routines within the standard library. But that wraps everything up. So thank you everyone very much. I realize I went way over time, and thank you all for your attention and everything. Yeah.
Is it on GitHub?
It is on GitHub, yes.
And it's completely free.
Yeah.
Is there any library like this for the newest version of C++?
Yeah, so C++23 added std stack trace, and that provides some basic ability to generate stack traces. It doesn't do anything with like tracing std exceptions or signal safe tracing or any other fancy things. For that, you might want to go to a third-party library, but you can generate a stack trace with the standard library. Yeah.
A clarifying question. The stack trace library is written using C++11, but
Oh,
I
yeah,
think it will work with
Oh,
any
yeah,
version of
sorry.
C++ at all, and even C.
Yeah. I do have a C interface for the library. Yeah.
I think a couple, when you were showing kind of like the inline functions.
Yeah.
Is there like, I think a couple slides ago,
Mhm.
is there like, kind of like any sort of, function, or is there a reason why it was the, inner, exception is, usually in that way? No, I'm not talking about this one. I'm talking about when you were doing for the, stack trace.
Oh, yeah. Or like one of the slides at the end.
Yeah. What's the frame?
Why this frame was blank? Or
No, I think it was a little bit after, you were showing like how this, how the CPG trace, or CPG trace track, unwinds into the two ones. You were showing like there was an inner, object.
oh yeah, that one. And you were wondering about the let's see, the like extra curly braces or that just extra try catch in general.
Yeah, the extra try catch. Is there a reason why you don't, throw, or you don't throw anything from there?
Yeah, so this try catch exists solely so that it can be considered during the search phase. And then when the standard library is internally calling do catch, that's when we generate the stack trace.
Okay.
Yeah, and the stack, crucially, the stack remains intact throughout the whole search phase. So we're able to get the stack trace from the exception that was thrown.
Okay, so this is just, this is just an empty one. There's no like.
Yeah, this doesn't actually do anything. It should never actually get caught. And as you can see, like the unwind interceptor is hidden away in the detail namespace, so users should never try to use it. Yeah.
Yeah, but would it be possible for the compiler to see that there's nothing in that catch statement and optimize out the search page for this, so it doesn't actually run the search page?
So I don't know if that would be legal, but in practice it doesn't. Yeah, Rob.
Question from online.
Yeah.
I heard a few references to glibc. Does the library work with glibc?
I believe so. I have not personally tested. Yeah. Question?
Yeah, I'm getting back to something you said earlier when you were talking. Unless I misunderstand you, it seems that debug fishing is a really bad idea because it requires you to retain your .o files in your build directory.
Yeah.
And the versions have to match your executable. Am I understanding that right?
So you're understanding correctly that it's a bad idea if you were to ship it. It's great for development though, because it makes linking really fast. Yeah. Question?
So I'm just a little bit confused about kind of like use case. Like I can see like in production systems.
Yeah.
It's nice to have all the stuff tracing.
Yeah.
But I know I just like in the high frequency trading something like when you're calling another function that might slow down just because a branch in cache.
Yeah.
I've done testing in production for some of this kind of stuff.
Yeah, so I guess for a little bit of context, so I actually use my library at my work. It is in production, including the awful universal tracing hacks. So far, it doesn't cause us problems. Yeah, knock on wood. But the cost you only pay when you actually try to generate a trace, when you actually throw. You would never like pay any of this cost in a hot loop or anything. It should never affect branch prediction. Exceptions in general are R0 overhead, you don't like pay any, there's no branches just because you write a try catch or anything. So yeah.
Actually, I don't think that that's the case for try catch. I think there is a, if you do have the try catch, there were some kind of small payments that are there.
The main thing you pay for is maybe a little bit bigger of a binary, but in the actual hot path of the function, there's no extra instructions or anything. Question?
Is there any special handling you need to do to support coroutine frames? You would jump in and out of coroutine.
That is a fantastic question, and I have not touched coroutines, and I'm scared to. And I, yeah, yeah, exactly, yeah. Alrighty, yeah.
I feel like you really want to talk about the extra traces.
Oh, not particularly. I forget why I added them.
Like 17 and 19.
Yeah.
They're yellow.
Oh, you know, I actually lied here. My bad. There's some like awful pragmas in here to disable some warnings. And yeah, I removed a couple things, but this was needed for like some shadowing or warning reason. But yeah, question. Yeah, I can. I guess send Rob the slides and then yeah, I can make them available. Yeah. I believe there was a recording, so yeah.
There's a recording. I'm going to gratefully ask Ali here to get it up for our YouTube page. I'll post any resources we get here as soon as they're available.
Alrighty. And if that's all, thank you all very much.